Welcome, everyone. Today, we are putting together the ultimate study guide to tackle one of the most fascinating topics in physics, that invisible, powerful link between electricity and magnetism. So if you've ever wondered how a compass really works, you're in the right place. Okay, so here's our roadmap. We're going to start with a surprise discovery that basically changed everything. Then we'll get into what magnetic fields actually are and see how a current creates its own invisible influence. After that, I'll show you a super handy trick called the right-hand thumb rule, and then, of course, we'll put it all into practice. So let's kick things off with the moment that connected it all. And it all comes down to a scientist named Hans Christian Oersted, and a bit of a happy accident. You know, back in 1820, electricity and magnetism were seen as two completely separate things. They were like two strangers at a party, totally unaware of each other's existence. But Oersted, well, he stumbled upon something that would change all of that. It was that simple. During a lecture, he noticed that whenever he passed an electric current through a wire, the needle on a nearby compass would just twitch. It moved. This was the first ever proof that an electric current actually produces a magnetic effect. Those two strangers, electricity and magnetism, they were finally introduced. Okay, so Oersted saw this magnetic effect, but what even is that? What is this invisible force we're talking about? Let's break it down and really get into the fundamentals of magnetic fields. The easiest way to think about it is like a magnet's personal bubble. It's this invisible zone of influence all around it. It's the region where that magnet's force can be detected, where it can actually push or pull on other things. And here's the really cool part. Even though we can't see the field itself, we can get a sneak peek. If you sprinkle tiny iron filings around a bar magnet, they don't just fall randomly. Nope, they trace out these beautiful patterns. And these patterns are what we call magnetic field lines. Now, these lines follow some very important rules. You're going to want to jot these down. First, they always emerge from the North Pole and loop around to merge at the South Pole. Second, they're always closed loops. They never just end. Third, the closer the lines are to each other, the stronger the magnetic field is in that spot. And last, and this is a big one, two field lines will never, ever cross each other. All right, so now that we have a handle on magnetic fields, let's zoom back to Oersted's experiment. What does the magnetic field around a simple current-carrying wire actually look like? What's really interesting is what happened when Oersted reversed the direction of the current. When the current went from north to south, the compass needle pointed east. But when he flipped it to go from south to north, the needle swung around and pointed west. This proved that reversing the current's direction also reverses the direction of the magnetic field it creates. And if you could see that magnetic field, this is what it would look like. Unlike the field around a bar magnet, the magnetic field lines around a straight wire are perfect concentric circles, with the wire running right through the center. So what makes this field stronger or weaker? It's pretty straightforward. The strength increases if you increase the current flowing through the wire. But it decreases the farther you move away from that wire. It's simple. More current means a stronger field, but that field gets weaker with distance. So we know a current creates a circular magnetic field, but which way do the circles go? Clockwise? Counterclockwise? Well, guess what? There's a super simple trick for figuring that out. This right here is probably the most important tool you'll learn for your study guide, so let's walk through it together. It's called the right-hand thumb rule, and it's a real game changer. Okay, so just imagine holding the wire in your right hand. Now, point your thumb in the same direction that the electric current is flowing. The direction that your fingers naturally wrap around the wire, well, that's it. That's the direction of the magnetic field lines. Simple as that. All right, now for the best part of any study session, actually trying it out to make sure the concept sticks. Let's see if we can apply this rule. Okay, here we go. Picture this. A current is flowing through a horizontal power line, and it's going from east to west. Using your right hand, what is the direction of the magnetic field at a point directly below the wire? Go ahead and pause here if you need a second to figure it out. So how'd you do? Let's check it. You point your thumb west in the direction of the current. And as your fingers curl around, you'll see that when they're underneath the wire, they're pointing directly south. So the answer is south. And here's one last thought to take with you. You can use the exact same rule to figure out the magnetic field for a circular loop of wire too. Keep practicing with that right-hand thumb rule, and honestly, you'll have this whole concept mastered in no time.